what page then?
2033. Oh, never mind.
71.
71.3, yeah.
Units squared.
So we just add up the, yeah.
Okay, yep, so you're got that.
It's going to be a lot of storage on your phone this morning.
You're between two curves, that kind of
You
thing.
can delete it after.
Okay, that's going to be. Okay,
Hopefully Miss Millie doesn't delete it before.
okay, because what I might do is. I've written notes for that in there, but that's okay. We'll just move on. Okay, so I've got written notes about it. So 71.3 was what we got when we added all those volumes. What we were doing was, quick reminder, we kind of like, for each of these, we looked at the heights, and then imagine if you took each one of these rectangles and rotated it 360 degrees around the x-axis, it would be a cylinder, and that's why we use the volume of a cylinder. And then so we worked out that the height of each cylinder would be 1, and we worked out the radius of each one, kind of by basically plugging those numbers into the function. Because what was the function? The function is like a linear 0.5x, and then we've got the height, the radius of each one, and then what we're doing is find the sum of the volumes of the 6 discs. So we took the height and the radius of each one, plugged it into the volume of a cylinder. So we worked out the volumes of the 5 cylinders. So 5 of them? Or 6? No, the 6. Worked out the volumes of these 6 cylinders that would be formed if you rotated each of these rectangles 360 degrees around the x-axis, and we got 71.27. So remember, this topic's called volume of revolution.
How come it's not how come it's a cylinder and it's not a
Okay.
no, not a cone, but not a square.
It's like a flat cylinder. It's like a cylinder that sits really flat.
But because it's a rectangle, wouldn't it be like a, you know what I'm trying to say? Not a square, but
No,
like.
like you have to think about it rotating from one point.
Yeah. So if this is Lauren's arm, then here's a rectangle, and then you rotated it around. Sorry, see the overall shape that would be made if this kind of like.
So what is
would be a
Lauren's
cylinder.
arm?
I'm the point.
She's the x-axis. Her arm is the
It's
x-axis.
only around one of the axes.
Yeah, it's around normally around the x-axis in our course. So it
Okay.
makes a cylinder,
Oh,
just
sorry,
a flat
X.
cylinder.
Higher level does the other one.
Yeah,
Oh.
let's take it again. Yeah.
Wait, so this rotates like this, like that,
Yeah.
or the x-axis?
Yeah. Around the
Oh,
x-axis,
okay.
yeah. And see how it makes a cylinder, just a very flat one. Very flat cylinder. So we worked out the volumes of all of those cylinders. Do you think the volume will be slightly higher than the real volume of the cone?
Yes.
Yeah, why would it be slightly higher?
Because the little rectangle is a little triangle above the little line.
Yeah, exactly. Each rectangle's
Great description.
the area of each rectangle is
cone.
slightly more. If you add up the sums of the areas of the rectangles, it's slightly more. So if instead you took this, so if you took each of these cylinders and rotated it, you would get like cylinders, of course, rectangles you rotate it. If you took this triangle and rotated it, what kind of shape would you get instead?
Cone.
A cone, yeah, exactly. So a cone. So that's eventually what we're getting to. I'll just try to go there a bit faster. Write down the definite integral you think can be used to find the exact volume of the solid of revolution formed when the triangle is rotated about the x-axis. Right, it's written down somewhere. Evaluate the integral and a GDC and compare it to your estimate. So basically we're trying to kind of prove that you can kind of do it with integration instead. And I'll kind of like try to. So notice that if it was just the triangle and you rotated it, this is a cone. So this is kind of pointing out the same thing. So this is a cone when you rotate the triangle. To find the exact volume of the solid of revolution formed when the triangle is rotated about the x-axis. That kind of thing. So, whatever, you can take the integral in general. You take the integral, and in this case, what's the lower limit and the upper limit for this one?
0 and 6.5.
0? I think it's just meant to be 6, yeah. So we'll say 0 and 6. What was the function again?
0.5x.
Yeah. And when you kind of rotate the triangle,
Times 4.
kind
Square
of square it, good, and because it's kind of
it.
circular,
And pi.
pi, chuck in the pi. So, but it's weird, isn't it? Yeah. So I'll just try to do it fast. So pi, and then sub in your formula, which was 0.5x. 0.5x is your actual formula of the line. f of x, so you stub in f of x basically. I'm getting to what we're getting down to the bottom. And then as Grace said, because you need to square it as well. It's like saying, in a way, it's like saying kind of pi r squared, isn't it? And then don't forget your dx as well. Dx. And you could just put a and b, but in this case it's 0 and 6 for this particular example, so we can put in 0 and 6. So now try putting that in your GDC now, using your nice integral function, and see if you get a number that's not too dissimilar to our value of 70 something. So let me write that down. And here it asks you to do it with integral calculus. Here it asks you to do it just in terms of a cone. Because you can see what the radius is, you can see what the height of the cone is, and compare the two as well. So grab our little calculators out. Seconds just math. Function int. What did you get, Sarah?
56.54866776.
Yeah, there's no way to put the pi at the front of the bracket, is there?
Yeah, HY, but you can.
Yeah, it's one we can do on here. So, what we can do is try, it's a bit lower, but we were expecting it to be lower, but I'm not sure if it was meant to be that much lower, but it's possible.
Lower than.
It'd be like, 70, remember the previous one was like around 70. It is possible, it could be a fair bit lower, because volume, if you change, like, if you have a little bit of extra area, you will have a much bigger volume. As in, like, a small change in area can lead to a large change in volume. So that is possible, because my answers I haven't quite written down yet, and they're lost in there somewhere. 56.5486, let's just put it down quickly, yeah. So 56.5 was it?
Yep.
Equals 56 roughly 0.5.
Unit squared.
Yeah. Oh, it's a volume this time. So what is it? As Paige said, cube. Yeah, it's cube because it's a volume. It feels weird, doesn't it? And here we're just going to use geometric formula to see what the volume of the cone would be. So if you saw it as a cone, what would have been its radius according to the thing on here?
3.
Yeah, it seems to be 3, isn't it? Yeah, because half of 3.5x, so that must be a 3, yeah. So radius equals 3, and the height of the cone, what is the height of the cone?
You said use 6?
Yeah, 6, yeah, we'll use 6, yeah. So how do you find the volume of a cone again?
Yeah, but in the exam, so you want us to make that inference?
Here it's just because it says use geometric formula.
No, but I mean because like you know how you just said use 6?
Yeah, I think on the previous page you can see it goes all the way to 6.
Okay.
Yeah, it just looks a bit funny on my.
Oh, okay.
What did someone say the volume of a cone formula?
No.
It's like a cylinder divided by 3.
So
Because it's
pi
heavier.
r squared h divided by h.
Yeah, and in the formula booklet I think they do 1/3 pi r squared h. So same thing. Pi r squared h divided by 3. Good. So we can plug that in. Pi. 3 squared. What do we get? That one out. It says I don't look at that. Sorry, I put the answers to the next page.
I got the same answer as the one above.
Oh, that's good. Okay, because I was starting to have doubts about the one above because I don't have my answers written down here.
Yeah.
Yeah, good. Okay, so that's good. That's made me feel better about the answer above.
Yeah.
Okay. So 50, is it that 56.5 roughly?
Yeah, it's the exact same answer.
Okay, good, yeah. And there's no meters or anything like that, so we'll just say units cubed. Fantastic. That's made me feel better. You know when you start to see an answer and you doubt? but this has confirmed it now. So basically notice kind of what we did. You take so in general, the little general thing we do, this is a wordy bit. So from the investigation we can assume that if y equals f of x is continuous between lower and upper limit, and the region bounded by y equals fx and the x-axis is between a and b, is rotated 360 degrees, or sometimes they call it 2 pi radians, about the x-axis. Normally in the exams I'll say 360 degrees, but don't forget 2 pi radians is 360 degrees about the x-axis. Then the volume of the solid can be given by, so what do we chuck at the
Pi.
yeah, there's going to be a pi. What do we, don't forget our lower and upper limit as well. But good that you're thinking of pi, a and b, and then the next thing, as Krista said, would be pi,
F of X.
yep, f of x, originally kind of put in f of x squared, good. So f of x, this is, I think it is given in your formula booklet. Let's double check. Squared dx. That's the general way. So pi, this is the original function, don't forget. So the original function gets popped in there. You're not doing anything to the function, you're not integrating it, differentiating it, you're just putting the original f of x in there. Yeah. Sometimes in the formula booklet, I'm not sure, maybe they do it like this. Similar way of doing it. You've got your a and your b, but instead of f of x, they might just put y. Yeah, exactly. Is that what they do, Sarah?
Pardon?
In the formula booklet?
Yeah, they put Y.
They just put y, yeah. So that makes life easier. But in case you're wondering what do they mean by that, this one, if anything, kind of makes a bit more sense to me. But that's the way it's kind of, it's pretty bad. So that's the way it's in the formula booklet. So let's make a note of that one. In formula booklet is this one. So it's good. You just use your little integration thing, throw a little pi in there. Remember, it was fine to put a pi in the brackets. In fact, we had to on the calculator, even though in our notation we pop it out the front. And so on. F of x squared, don't forget to square the f of x. It's kind of like pi radius squared, and think of the radius as being your function. Which feels strange, but how it's done. So we're now on to page, the next page is just a few more pictorial examples of how you can get different volumes of revolution. So nothing to write on the next page, I'll just quickly read through it. So these are just some pictures just showing you graphically how it looks. Consider the curve between A and B. So if you had an x, what kind of function do you think this one is? Exponential, good, exponential. Area under an exponential makes these kind of things. If you rotated it 360 degrees around the function, you get this funny looking megaphone kind of shape. Yeah. Sometimes they call them solids of revolution, but volumes of revolution is the general terminology. Other ways of revolving, Grace was talking about it, like in high level, they'll kind of tend to do a bit of rotating around the y-axis as well.
Oh, really?
In our course, it tends to be just around the x-axis.
Wicked.
Well, around, yeah. In our course, it is around the x-axis.
You just say 3D math.
Yeah, it looks quite cool, doesn't it? So similarly, if the part of the curve is rotated about the y-axis in a solid of revolution will also perform. However, in our course, we deal with volumes of solids only around the x-axis, but in high level, as Grace said, they could do y-axis ones as well. Pretty cool. So let's just do 2 quick examples. I've actually got the answers for these ones, which is good. Find the volume of the solid formed when the graph of the function, a nice one, y equals x squared, for that thingamajiggy is revolved around the x-axis. If you want, we can do a really quick sketch. Where if you want to, you can go straight to working out the answer. Got your x, got your y. Y equals x squared, what kind of function is that?
A U. Oh, it's a quadratic.
Yeah, and it's a quadratic. And notice it's just from 0 to 5. So just this bit, it'll be kind of, it's got a y-intercept of 0. So y equals x squared just kind of goes like this, doesn't it? So there's your y equals x squared. And then if you rotated it 360 degrees, and it's from 0 to 5, so let's just do it from 0 to 5. So notice we didn't bother with the negative part because it just said from 0 to 5. So if you rotated it around the x-axis, what kind of shape would it look like?
Another megaphone?
Yeah, a curvy cone kind of thing. Curvy cone, a megaphone-y kind of thing. Some people think it looks like a speaker, like a little speaker cone. It's a shocking picture. I'll show you. Like meaning like this kind of thing, basically. Just pointing out what it looks like. Some people, when they draw it, they do this, and then they mirror image it that way, and then just kind of do a circle. So do that, mirror image it that way, and then kind of do a vague circle here. That's kind of how it will look. Nice. So yeah, it's in like here's the whole side of it. And this is like the opening of the speaker cone here. That can help just to visualize what it might look like. Out of interest, what is the coordinate up here? What would be, so this 5, yeah? What would be the x value?
Sub it in there.
Yeah, sub it in there. What's 5 squared?
25.
Yeah, so that's helpful to know. Maybe that might be helpful. Maybe it won't be. Might be helpful for working out the radius at least. I don't know if you need it. So the volume of the revolution. Some people take the pi out the front. Another thing you can do is, in the other textbooks, I'll just show you what's possible. So the volume equals, some people put the pi out the front, because pi is just a number. And remember when you've got a number, like a factor of the whole thing, you can just pop it out the front. A, B, F, some people go just y squared dx. That's a general formula. So if that's nicer in the calculator, it worked anyway when we shoved pi in it, but maybe this is a better thing to do, pi times all of this. Just reminding us we can do that as well. So then pi 0.5, sub in your x squared, and then don't forget we've got to square it. X. And if you want, pop that in our calculator. You can do it by hand if you want, but that's too messy. Practice popping it in your calculator. Oh, does it? That's nasty of me. So to do it non-calc,
Next.
I put the bird, yeah. You can do it with calculator if you want, just because we're a bit pushed for time with my
Well, how am I
stuff at
supposed
the
to
beginning. I'll show you how to do it. Yeah,
Square brackets.
yeah. So you have to do pi times by, yeah. What is the integral of x squared?
Oh, 3, no,
X
2x 1 over 2.
X cubed over 3.
Yeah, x cubed over 3. So it is good to practice that. So notice it's pi times this between 5 and 0. So if you were to do it by hand, that's what you would have to do. So you would then do pi brackets, and then inside there you might just put 5 cubed over 3 minus 0 cubed over 3. So see how it's still just pi times the answer to all this kind of stuff. And I'll let you know. You get something like 625 pi cubic
Wait, but what
units.
do you do with the square? The way it says x squared squared.
Oh, hang on. Oh yeah,
Don't you
What
have
did I
to
do?
multiply that into the x root?
I did. Yes, sorry, Grace. Thank you so much. Yes, exactly. See the original one? It's x4. Sorry about that. Notice that the only thing you have to change is you put a 4 here and a 5 there. A 4 here and a 5 there. Thank you, Grace. I wasn't even looking at what was written. So that thing is x to the 4. See that x to the 4? So then the integral of that, as Grace said, is x to the 5 over 5. So sorry, just change that to an x to the 5 over 5. And then, so I'll change this to a 5, 5, 5, 5. So you just need to write over what you'd already written. Thank you for noticing that. And then 5 to the 5 divided by 5, would you agree that's the same thing as 5 to the power of 4?
Mm-hmm.
So what is 5 to the power of 4?
125 times 5.
Yeah, 125 times 5, which is?
625.
625. So if this was non-calc, you could write 625 pi cubic units, units cubed, whatever. Quite often they're just happy with the number, to be honest. Because when it's units, quite often you don't need to write anything. Some people like to.
Miss Melanie, why did you change the 3 to 5?
Good point. Because as Gracie pointed out, I did it as if it was just x squared, and Grace reminded me, like, hang on, you've got to square the function.
Okay.
Yeah, so because in the formula it's a function squared, whereas I just did it, I forgot to do this square bit. Yeah, and then x squared squared is just x4, and then you integrate that instead. Because there wasn't much space to rewrite this whole thing again, I thought I'd just write is x4, and then we integrated x4. So and that's something I sometimes forget. I forget the fact that I've got to square the original function. I go straight into integrating. That's a thing I miss sometimes. Even though I had the answers written around the
You know people leave and they come back and just like minute you.
So 625. Find the volume of the solid form where the area between the curve y equals x squared plus 2. What kind of function is that? Quadratic. What kind of transformations happen from an x squared?
It goes 2 units to the left.
Good guess.
Nope. Okay, never mind.
Up.
2 units to the right. I mean 2 units up, like Sarah said. Yeah, in the brackets. When it's in the brackets is when it's moving sideways.
I'm just gonna stop guessing.
So good that you're thinking about it. So the area between that, so it's just an x squared shifted 2 units up from the x-axis. This is the lower limit, upper limit, is rotated through 2 pi radians. So what does that mean?
360 degrees.
Yeah, 360 degrees. So this is just trying to present a similar one, just written in a different way. 2 radians is 360 degrees. If you wanted to draw, sometimes it can be helpful, just have a little look, see does it make sense. X, Y, quick sketch. So x squared, and it's between 1 and 3. So x squared plus 2 is x squared plus 2 is like this. It's up at 2. So y equals x squared plus 2. And notice it's only between 1 and 3 that they want it done. Starting to lose our calibration. So just think the area is this bit here. So it's going to be one of those kind of megaphone kind of ones. So it's basically as if that yellow area got rotated 360 degrees around the thingamabobby. And we just do the same thing as above. We can do it non-calc if you want. If you hate doing non-calc, we can do it with calc if you want to do it faster. I'll very quickly calibrate because it's time to go already.
We have 25 minutes.
Oh no, I think she meant the calibration is going.
Yeah, the calibration's dying. It's going out of whack. So nice. So volume. Our volume V is do big integral sign. I know I do sometimes. Yeah, like putting the pi out the front is possible. So if that makes life easier, pop it out the front. Just particularly to do it by hand, it's nice to put the pi out the front because it's just a factor of the whole thing. So you can pop it out the front. And then y squared dx. So we've got to remember the square thing. So remember like before I forgot to square? And then Grace had to remind me. So it's like x squared plus 2 squared. Yeah, good. Squared.
So would that be if you like?
Yeah, what would that be? You would need to, that's a nice quadratic, so just FOIL it. If you're worried about space, I'll just do it up here. X squared plus 2, just so you can see it all on one page. FOIL all that business. What does that give us? X squared times x squared?
X4.
Good. X4. X squared times 2.
2x squared.
X squared times 2.
X squared is 4x squared.
And the constant at the end?
4.
Plus 4, yeah. Good, so we've kind of worked all that thing out. So if you want to be nice and thorough, you can do all that Bizzo 3, 1. And then it's x4 plus 4x squared plus 4 dx.
And then
you can go
fast in math.
Yeah, it's a nice one to go. As I said, the last one's just kind of like more word problems. The same maths, but it'd be good to like talk to you.
Is that S or is that phi?
That's a, oh
Pi.
gosh, that's a pi. Thank you, Ron. So that's meant to be a pi. Where did I get S from? Okay, so pi. I had a big fight with a photocopier before, so that's why I'm a little bit frazzled. Trying to get these things out of the jam. So that was meant to be a pi, sorry. So now we need to just pop the pi out the front and then do your square brackety stuff. We've got to integrate the thing that's in there now.
X5 over 5
X5 over 5.
plus
Yep.
4x cubed over 3.
Yep.
Plus 4x.
4x, well done. Good. Nice work. And then 3, 1. And then if you want to do it with calc.
No, we can't. It says no calculatrice.
Yeah, true. It's like it's for punishment. Okay. So it's like x5, oh gosh. So 3, 5 over 5. 5 is just 1. 1 cubed is just 1, so 4/3.
Aren't you supposed to do the upper one first? Okay, you did.
Yeah, and that's true. Yeah, you do. So because, like, you know, 1 cubed is just 1, 1 to the 5 is just 1, I just went straight to that because I'm running out of space. Okay, that's 3, 5 to the 3, gosh.
80, well, divided by 5 is 81. 243 divided by 5.
243 over 5. Yeah. So let's leave them as fractions for now. It's good that you guys want to practice your non-calc.
Oh, just doing this non-calc.
Yeah, do it with calculator is good too. Good to practice both.
Well, 3 to 5.
So 3 cubed over 3 is going to just become 3 squared. So plus 36. And then minus. We need a common denominator, don't we? So common denominator would be 15ths, would you say? Okay, so 3 15ths plus 20 plus 60 over 15. Yeah, this is a yucky non-calc one. Hideous. You don't want to just tell me the answer. I'll let you know. It's meant to give you 1366 pi over 15. Let's get to the point where I'll just tell you that's the answer. And so we basically have to add those two together, turn that into something over 15, and then or combine this as well. But mind you, this might kind of simplify. That would give you 83 over 15.
Mm-hmm. That gives you 5 from 5
Yeah. So we have to keep this as something over 15 and add it together. That's a pretty hideous non-calculable one. But you realise roughly how you would do it?
Wait, how'd you get?
And so you need to multiply the top and bottom here by 3. So you get 48, or turn them all into over 15, which is pretty hard for non-calc. So I think, like, you know, it's unusual if you get something like that non-calc.
How'd you get that big number?
So, okay, so this one just becomes something as simple as 83 over 15.
Yeah.
But this one, you've already got 36 plus 12, which is 48. And then you've got to times the top and bottom here by 3.
But
Well.
even if you simplify this, that becomes 81. But 81 plus 36 plus 12, that gives you 129 and 120.
243 divided by 5 is a big number too. That's another thing. So 48.
46.
Yeah, so that's probably why you're going to get a big number like this. But yeah, feel free to do that if you want, but I feel like because that's really hard and what you need to do. So then, yeah.
But
Okay, to go
this
to the
doesn't make
next one.
sense.
Yeah, this is going to the next one. So these are just yeah, they're kind of very yes please. Okay, so these are because really probably like that's pretty extreme in our class in our course. So we may as well just move on. These are just, as I said, word problems, just practicing them with velocity, acceleration, all that kind of stuff. I've back to IB1 Calculus and also page 3 of this booklet, where we discovered how differential and integral calculus can be applied to linear motion. So I'll quickly do this because this is recap. Answers for these ones. Should have been somewhere. Okay. Nope. Not there. Not there. They're here. Nice. Okay, so like differentiation, integration can be applied to motion problems, e.g. problems to do with displacement, velocity, and acceleration. You probably know them, so we'll put through that. This kind of application is commonly found in physics. And what's it called again?
Kinematics.
Kinematics, yeah. Okay. For example, if velocity is the original function, then the integral of velocity, you're going a step up from velocity, will be
Displacement or
displacement, yeah. So yeah, this paragraph is good to think about because this is the kind of one where it's easy to get muddled. Like integrate, it goes displacement, velocity, acceleration. So if you're integrating, you're going the other way up. So integral of velocity is displacement. Because sometimes you've got to decide, hey, do I need to integrate or differentiate to get this function? If acceleration was the original function, then the integral will be the velocity, yeah. Yeah, so those things are helpful for you to remember. And then just for harking back to if it was a derivative instead, if the original function is velocity, then the derivative, what would that be of velocity?
Acceleration.
Yep, acceleration, the next one down. If the original function is displacement, then the derivative will be the
Velocity.
velocity, yeah. So basically, as you're going down this way, it's differentiation.
I always forget the verb for differentiate.
Yeah, differentiation. And if you go in the reverse, what's that one called?
Integration.
Integration, yeah. Another word for integration is anti-differentiate. So don't forget that word too. Anti-differentiate. The normal words we use are integration. But another word for integration is anti-differentiate. Just don't mind it's the wordy bit.
We're just telling you about the test, sorry.
Yeah, sure.
It's lesson 6, 7, and 8 from derivative.
Yeah, like remember like graphs of derivatives?
Mm-hmm.
That kind of stuff, like graphs of derivatives, there's finding second derivative test, points of inflection, maximums, minimums,
Okay, and then for the
just a bit of that.
integration part
And a lot
up
of
to
integration. The whole integration stuff we've done. So
all
all
that
of-
we've done.
Yeah, all of chapter, what is it? Chapter
9.
9, thank you, chapter 9. All of chapter 9.
Okay.
It'll be mainly chapter 9 stuff, to be honest.
Wait, that's
But-
chapter 6, 7, 8.
No,
Chapter
lesson
7, lesson 6, 7, and 8, and chapter 9. So yeah, so it's also up on there. But it'll be mainly the integration stuff, to be honest. There'll be a bit of the graphs of derivative stuff, like in the topic assignment. So looking at your topic assignment would be good ways of revising that 6, 7, and 8 stuff as well.
Okay.
Hold on. Okay, so I'm just looking at that. Okay, so if the velocity, you'll do just fine. If the velocity of a particle is given as v of t, what is the distance traveled? Distance is similar to
displacement.
displacement. Yeah. So do we need to integrate or
Yes.
differentiate?
Integrate.
Integrate, good, yeah. So integrate v of t to get distance. We'll call it distance d of t, or some people call it s for displacement. It doesn't matter what you call it, to be honest. Like they just want the function. So what's the integral? So integral of 3t squared dt.
3t 3 over 3.
Yay. Equals good. 3t 3 over 3. What am I doing? Yeah, you're right. 3t 3 over 3.
And then you get 9 divided by 3.
Oh, that simplifies, by the way.
So just t over 3. t3.
Yeah, t3. Yep. t3, and then you can do that bizzo. And what are our upper and lower limits?
0 and 2.
With 0 and 2, yeah. So if you want, you can just put them here, that's okay. 0 and 2. Notice there's no need to put plus c because we're working out a definite integral because we've been given the lower. If they just said find the function, they didn't give us the lower and upper limits or anything to calculate, we'd need the plus c in there. So this is a nice one, calc one. And then what would I do next?
Then you do t, 2, and then cube subtract 0 cube.
Good, yeah. Equals, what do you get?
8.
8, yeah. 2 times 2 times 2. What's our units in this question?
Meters.
Meters, good. Because it was meters per second for velocity. Distance travelled. At this is just meant to be a simple question where you're not thinking about anything negative or positive. Distance is a scalar, so no direction. There's no negative, positive. And in this case, it's just a simple one. You don't have to think about below the curve, above the curve. It's just a nice simple one. Below the x-axis, above the x-axis. Yeah, so another. Is that okay? Okay, good. So a little bit slightly more complicated. This is nice because it kind of ties in a few, like the good thing about the word problems is it's kind of like reviewing at the same time. The displacement function, so displacement function, for a particle moving along a horizontal line is given by this thingy here. What kind of function is it, by the way?
Quadratic.
Quadratic. What's its y-intercept?
Plus
Plus 4. So what's the initial displacement? Just by looking at that.
4. t2 2 jack minus.
initial display at the initial
Oh,
displacement,
0.
time is 0. So at the initial displacement, time is 0. So if you subbed in 0, what would be the
Plus
displacement?
just before.
Yeah. So at the very beginning of time, how far away was the particle from the origin?
4 meters.
Yeah, 4 meters or 4. Yeah, it's meters, is it?
Mhm.
Yeah, meters, good. So see, at time 0, the particle is 4 meters to the right of the origin. Because if you type sub in t is 0, that's meant to be a t, by the way. Sorry about that. That might be throwing a few people, or maybe not. So that's a t. Sorry about that. 2t squared minus 9t plus 4.
Wait, so what does the S mean?
Displacement. So
Like
S tends to,
distance?
yeah, like distance, displacement takes into account direction. So if I moved, this is a good point. If I was here and I moved 1 meter this way
Yeah.
and then 1 meter that way, what distance have I travelled?
2.
Oh, sorry. If I move 1 meter this way, then back,
3.
and 1 meter that way, I've travelled 3 meters in total. If
So
I,
the distance will be 1.
yeah, so if I went 1 meter this way,
Would be one, but your distance.
and my
Wait, so the last
displacement,
question asked about the
my
distance.
displacement would be,
Your displacement will only be one.
yeah,
Sorry.
and displacement takes into account negative and positive.
So it would be 3 then.
No,
No.
displacement
Negative
is
one.
from
Negative
0
one, yeah.
to wherever you end up. Distance traveled
Okay, yeah.
includes everything.
Yeah, distance
So,
is just like, doesn't matter whether anything's positive or negative. It's, in real life, what distance did I travel?
So the last question asked about the distance.
Yeah, just the distance, yeah. So there's nothing to, but later on we're going to have ones where we're going to have to take into account something being negative, something
But I
being
thought-
positive.
So we integrated the
Displacement.
velocity,
Yeah, which is really more just like the speed.
which
it
means that
dodgy,
we would
was
get displacement, but you're just telling me that displacement and distance are two different things.
When
Well,
we get into
it's-
these ones, you're going to take into account. So do you understand the difference between distance?
Yes.
Yeah, okay, good. So as in like from here to here I've gone 3 meters distance, but from here to here my displacement is negative 1.
So
Yeah.
distance
Basically,
from starting
From where
point.
you started, from where you started,
Okay.
yeah, total distance. And distance is just always positive. Displacement can have negatives in it. Yeah, distance is like absolute values. Like remember when we kind of did areas under curves and anything under the curve we had to make it positive? If we
That was
talked
the
about the
area?
areas, yeah, the shaded areas, it's that kind of stuff. So that's going to start to come into effect here, but in the previous one it didn't. So the displacement for a particle is moving along, so it's that one. Where t is measured, t is greater than 0, that's important. T is measured in seconds and s is measured in meters. Find the velocity of the particle at time t. Do we need to integrate or differentiate?
Integrate. Differentiate, sorry.
Yeah, differentiate, good. So this is good practice of like, now that we know
Yeah,
more
right.
things, it's harder to know what to do because you know more things. So we need to find, so differentiate S of t. That thing. So S of t, so S of t, if you want, make a note that it means V dash t. No, what am I saying? V dash t equals S dash t. Vt. V of t is equal to S dash t. You don't need to write equals S dash t, but if you want to for your own reference. So velocity is the rate of change of that thing. Remember differentiation, the derivative means like the rate of change kind of thing. So if you see the word rate of change, it means the derivative, that kind of thing.
Yep.
So what would be the formula then?
14 subtract 9.
Yeah, 4t subtract 9. Find the velocity of the particle at time t. They didn't ask us to sub in anything for t, they just wanted us to work it out. So it's that thing. 4t minus 9, that's the velocity. Find when the particle is moving left and when it's moving right is a little bit more complicated.
Oh.
Yeah, when is it moving left, when is it moving right? So, velocity, notice at some point, so the velocity equation, sometimes it's helpful to imagine the graph. The graph of the velocity, when the velocity is negative, it's moving left, and when the velocity is positive, it's moving right. X, Y. What kind of function is this?
Linear.
Linear. So, it's going to have a y-intercept of -9. It's kind of going to look like that. So what's crucial to know, where is the turning point? Where did it change from positive to negative? Is that little point there. At the x-intercept or the t-intercept. What is the value of y always at the x-intercept?
0.
0, yeah. So take your 4t minus 9, set it equal to 0. And what would that give us? 4t equals 9.
9/4.
Yeah, 9/4 seconds. Some people prefer to call it, or 2.25 seconds, whichever one you prefer. So that's important. That's a helpful little thing to know. 9/4 or 2.25 if you prefer.
Or this is a graph of the derivative. So it's negative and the y by is a negative.
Second what? Second, wait, what does it say?
Seconds.
Or 2.25.
Or 2.25 seconds.
Oh,
9/4,
oh.
yeah, sorry, yeah, it's a bit messy. 9/4 is 2.25. If that's an easier number to deal with, you can use 2.25, 2.25. So find where the velocity is 0. So notice what we've graphed is we've graphed v of t. Just that might be worth noticing. We've graphed v of t. So when the velocity is 0 is kind of where it changes direction. So when is the graph moving left? When is the graph moving right?
Wait, so is the graph moving left when it becomes, yeah, never mind.
Yeah, it's moving left.
When it becomes negative.
Yeah, sort of here.
Yeah.
Oh, and it's greater, yeah, time greater than 0, so that doesn't even come into account, taking into effect, yeah. So it's moving left when it's negative,
Wait, why did you just cross
So
because it's t is greater than 0.
So technically on
Yeah.
x-axis is our t-axis.
Yeah, so in a way that's more like the t, you're right. The t, if that makes more sense. So it's moving, moving left, you might want to make a note, moving left here, moving left here as v of t is negative, and it's moving right here as v of t is positive. So finding that little point where they change is important. Here as v is positive. Nice. And so, oh yeah, and then we need to say our answer. So our answer is like an interval. So it's where is it moving left, where is it moving right? So we could finish our answer by just saying it's moving left. Moving left, would you say for t values, less than
9/4.
9/4, yep. Moving right for t values greater than. T values greater than 9/4. It's kind of how we could write our little final answer. The motion diagrams aren't such a biggie, like you don't really see them in tests. But I'll just do it quickly for you to point out kind of how you do it. Motion diagram, yeah. And notice that motion diagram, it's displacement. You don't really seem to be asked to do motion diagrams in exams. So here's our
So
0.
will we be asked?
Probably not, yeah. So, it always happens at a certain time, doesn't it?
Always happens when it's always like to be.
Yeah, exactly. To be honest, like what I've shown you is probably a fair bit. Like what I've shown you at the moment is most of the stuff.
We were almost there.
I know, but you probably want to pack up, don't you?
No.
No? Do you want me to just quickly close it and try to open it again?
Yep.
Okay,
Where
sure.
did that go?
You know how the thing stops writing? Windows cannot access, that's great. Great.
Good job.
And then you'll see the bit where I'm moving it.
I don't think we've ever moved so fast in that.
Yeah, it's not ideal. Like it's nice to stop and ask questions. But like just get you guys some practice. Oops.
Great. Economics. That's great.
So this is a really fast version of it. So notice it's a motion diagram's a displacement. So you've got 0, you'll need to go up 2, 4, 6, -2, -4, -6. I just know this because that's the answers. So motion diagram, I'll show you what it looks like. At time 0, how far was the particle from the origin again?
At what?
At time 0, well, how far was the particle from the origin again, from that thing we said at the top? 4 units, yep, to the right, yep. So remember at time 0, when you sub in time to the displacement function at the top, so that's time 0. So, because notice this is like meters. So we're not talking about time here, so put it at 4. And then at the beginning, was it moving left or right?
Left.
Left. And if you sub in S of 9 over 4, or S of 2.5, I'll just let you know, if you sub in 9 over 4 into the displacement, you get negative 6.125 meters. So what it did was, the little particle went left until it hit negative 6.125 meters. That's roughly here. And then it turned around, you know, just continues on.
Wait,
Right.
so is that for the derivative?
That's at t equals 9 over 4 seconds. So this is S of t. So what it did was it was 4 meters from the origin, then it moved down to here, down to negative 6.125. If you plug in time at the time at 2.25 seconds, you get negative 6.125, which is that thing. And then it turned around and turned right after that. But you don't really motion diagrams. Some people just say they find them helpful. I think, do you have to do them in physics?